Okay, before I go through the first example, I want to go through some limit laws that we're going to be using on a few problems, just so we know what limit laws are. When we do limits, we're going to be doing them more like examples 2, 3, and 4, where we're going to come up with some algebraic technique to simplify the expression to somehow get where we can put the number in. We're going to be using law number, well, none of these laws. But there's one extra law I didn't print. You can put it at the bottom. It's a short one. But anyway, suppose c is a constant, the limit f of x as x approaches a and g of x as x approaches a exists. So we're assuming some stuff. Anytime you see c, that's a constant, like any number, like 5 or 10 or -2, 1/2. The limits of f of x and g of x do exist. These are required for these laws to be valid. Okay? So if at any point a limit of f of x or g of x doesn't exist, remember if the left-hand limit and the right-hand limit don't reach the same point, that would be a discontinuity where the limit does not exist, or if there's an asymptote, another asymptote going different infinities, the limit does not exist. So if that happens, we don't have to consider these laws valid. But other than that, we're just assuming every one of these has valid laws, valid existing limits. So the graph might be something like this. Maybe it has a hole in it and continues on. That limit exists. So that's what f of x and g of x as x approaches a look like. All right. The first one and the second one basically are the same law because after algebra we realize addition and subtraction are basically the same thing. Subtraction just addition of a negative number. But it's saying if you have the limit of a sum of functions, it's the same as the sum of the limits of the functions. All right. What that allows me to do is if I have a polynomial made up of multiple pieces, I can limit each piece individually instead of having to limit the whole thing at once. Same if it's minus. So the purpose of that, these two rules, is if I have limit as x approaches, let's say 3 of x squared minus 2x plus 7. These first two laws allow me to split this apart into the limit as x approaches 3 of x squared minus the limit as x approaches 3 of 2x plus the limit as x approaches 3 of 7. All right, we can break it apart into separate limits, limiting each different piece instead of limiting the whole function at once. So that's what these first two laws are for, is to split limits apart. All right. This third one says if there is a number times a function of x, you can pull the number out in front of the limit. So here's an example of that, specifically right here. Notice there's a number being multiplied by x. X is a function of x. So I could, for that piece, say minus 2 limit as x approaches 3 of x. All right. This is a multiplication. If you have, let's say, limit of x sine of x as x approaches 2, you have a limit of a product. You can break it into the product of the limits. So limit as x approaches 2 of x times limit as x approaches 2 of sine of x. And similarly, if you have a limit of a quotient, you can break it apart in limit of the top over limit of the bottom. There is a disclaimer for this one. Limit of g of x as x approaches a cannot equal 0, otherwise you're dividing by 0. All right, so if that happens, it's not allowed. But other than that, it's allowed. So basically, all these laws are just to be able to break down functions into individual limits that are easy to do. You're going to see in the next set of limit laws that limit of x as x approaches 3 is simple. Limit of x squared as x approaches 3 is simple. Limit of 7 as x approaches 3 is simple. We're creating a situation where we can evaluate pieces based on these laws. All right? Continuing on, the next set of laws. And this is the last one as far as creating new things, and then everything else is more evaluating things. If you have limit of a function to a power, that's the same as the limit of the function evaluated first raised to the power. So what that means, suppose limit of 2x minus 7 to the third power as x approaches 4. So we have that problem. This is telling me I can do the limit of 2x minus 7 as x approaches 4 to the third power. I can figure out what this equals first, then raise the answer to the third power, instead of raising this to the third power, then putting the limit. All right? Now, the last 5 laws tell us how to evaluate a limit. All right? Limit of a constant is a constant. This is the easiest problem in the world. People miss it. for whatever reason. I don't know, maybe I'm confusing people. Maybe on the first 6 laws are making your brain kind of process at some weird rate or something. But let's pretend nothing's happened yet today. Becky, pick a number.
5.
Logan, pick a number.
8.
If this is a number, any number whatsoever, and this is any number whatsoever, doesn't matter what the numbers are, but if they're both numbers, the answer is whatever that number is. Doesn't matter. Because this is the function we're considering. F of x equals 5 is a horizontal line at a height of 5. No matter what x value I'm getting close to, the height of this function is 5. It doesn't change. This is a constant function. The answer is going to be 5, no matter what this number is. Go back to this other page. What does that equal? 7. Because it doesn't matter what this number is, it matters what that number is.
But if it was like 7x, if it was Li and then 7x, like that is.
If 7x, that's not just a number. Right now it's got an x on it. We got to get into a different one off of that. But if it's just a number, the answer is the number. So that's just 7.
All right.
Okay, it's just that easy, I promise. So if it's a constant, the answer is the constant. No matter what x is approaching. If x is approaching infinity, the answer is 5. If x is approaching hippopotamus, the answer is 5. It doesn't matter what it's approaching, the answer is 5. But this is a 5. That's 5. All right? Number 8. This says if you have the limit of x as x is approaching a, the answer is a. A matches what? A matches that number right there, right? So if we have an x here, and x is approaching some number, the answer is whatever that number is. So in other words, limit of x. Renee, pick a number.
2.
We have the limit of x. X is a straight line, right? With a slope of 1 going through 0, 0. Whatever x is, y is, right? And the answer we're looking for is y. X is approaching a value of 2, so y is approaching a value of 2. If we're taking the limit of x, the answer is whatever x is approaching. Every single time. Go back here. What's x approaching?
3.
So what does that equal?
Equals 3.
That equals 3, and that's being multiplied by negative 2, so altogether the answer is negative 6 off of that term. All right, so that's all that limit law is telling us. This one, if x is being raised to a power and x is approaching a, we're simply going to get a to whatever that power is. For example, limit of x cubed as x approaches 4. All right, x is approaching 4. 4 cubed, which is 64. That's all limit 9. Now it says n is a positive integer. It actually works for any power. If it's like a cubic or a cube power, like 1/3, or if it's like 7/13 power, it would work. It wouldn't be very friendly, but it'd work. All right. The reason they say n is a positive integer because here this is where it gets the fraction of power idea. But basically, these are the same rule. A fractional power, a radical is just a fractional power. But anyway, limit of the square root of x as x approaches 16 is
Square root of 16.
square root of 16, which equals 4, right? So again, that's all that's saying. If you're doing the limit of a radical as x approaches some number, you change x to that number and evaluate the radical. Okay, evaluation of limits going on. And finally, if you have some function of x, some nth root, so let's say limit, let's say the cube root of 2x minus 3 as x approaches 6. That's not what I want to approach. Hold on. As x approaches 15. I have a nice answer. Okay. So 2x minus 3 is a function of x. So it tells me to do f of a, which means to evaluate this at a, which is 15. What's 2 times 15 minus 3? 27. Cube root of 27 is? 3. All right. So let's look at example 1. There's going to be homework problems like this that say evaluate the limit and justify each step by indicating the appropriate limit law. There's several homework problems like this, 3 or 4, I can't remember how many, but there's not a whole lot. Okay, for this specific homework section, I do expect you to identify the limit laws you're using. You don't have to write out the laws, just say number 1, number 3, number whatever. All right, whatever ones you're using, write down those numbers. You have the yellow sheet there in front of you that has those. on it, okay? There will be a quiz question that I ask you to evaluate the limit and justify each step with the limit laws if I remember right. I might be wrong, but just let's pretend there is one, so practicing on a homework would make sense, just in case that a quiz question should come up, or maybe a test question from chapter 2, I don't know. It's something in the back of my mind tells me that one of these happens on a quiz or a test. I seem to remember, so doing it a few times here wouldn't hurt you. This is not the way we're going to do limits most of the time. Usually, we're just going to evaluate it by substituting the number in. We're going to use the simplest limit law, which is going to come up after this slide. All right, so what I'm looking at here is a limit of a product. If you look on your sheet at rule number 4, limit of a product. It says do limit of the first factor times limit of the second factor. So that's rule number 4 that we're going to use to split it apart. So limit of x cubed plus 2 as x approaches 3 times limit of x squared minus 5x as x approaches 3. That's rule number 4. All right, and again, the requirement of that rule is that our limit argument is a product of functions. So I'm multiplying two things together as the argument. I can split it apart into two separate limits. Next, use some different colors here. Let's go with purple for that one. Actually green. All right. This blue limit, it's limit of x cubed plus 2. That's the limit of a sum, right? And the very first rule says that limit of a sum, I can break it into the sum of the limits. Keep in mind, this is one object, this blue object here. If I make it into limit of x cubed, or as x cubed as x approaches 3, plus limit of 2 as x approaches 3. If I do that, how many terms is this now? 2. Okay, and I want to multiply that times the green thing, right? So since I broke this one thing apart into two separate things, I notice I'm going to put a bracket or parentheses around it to treat it as one object. If I do the same thing to the green one, this is limit of a difference. Okay, I'm going to change it into limit of x squared as x approaches 3. Now I'm going to do one other thing on this second one. It's minus 5x, right? I'm going to make minus 5 limit of x as x approaches 3. Kind of combined a couple rules in that. All right. Once again, I changed one thing into multiple things, so I'm using a grouping symbol to group up the two things that became out of the one. Now, let's look at the rules I used on this one. The subtraction one, going from here to subtraction, is rule number 2, right? And the 5 times x, moving the 5 out in front, is rule number 3. The addition one I used here is rule number 1. So altogether, I used numbers 1 and 2 and 3. So 1 was the blue one. The addition changed from the limit of a sum into the sum of limits. Rule 2, limit of a difference into the difference of the limits. Rule number 3, taking the coefficient out in front of the limit. Okay? Look at the pieces I have left here. I have x to a power, I have a constant. I have x to a power, I have a constant. Or I should say I have to have x being multiplied by a constant. Okay, so looking at these rules here, these evaluation rules, let me erase all this graffiti that I got on here. All right. I've got limit of x to a power, that's rule number 9, I can evaluate it, right? I've got x, I can evaluate it. I've got constant, I can evaluate it. Those are the types of things I have left in this expression now, so evaluation is possible. For constant, the answer is the constant. For x, the answer is the number it's approaching. For x to a power, the answer is the number it's approaching to that power. So looking at what we have, every case, the number it's approaching is 3, right? So looking at these rules again, I'm going to go to a little page here so we can see them while we do it. All right. So this one here, I'm going to use rule number 9 because I have x to a power. The rule says the number it's approaching to that power, so that there becomes 3 cubed. This one here that's a constant, limit as x approaches the constant, or limit of a constant as x approaches anything is that number, so the answer is 2. That's still in brackets, because that has to be evaluated, right? And then, if we look at this piece here, that's the same as the one before, we have x to a power, so it tells us that we're supposed to get that number to the power. And then, if we look at this one here, minus 5 is just there, limit is of x as x approaches a is x. So this piece here equals 3. It's being multiplied by 5. Okay, I just use rules 7, 8, and 9. Again, this 5 was just there, minus 5 being multiplied by the limit equals 3. All right, so that's what happens there. At this point, I'm done using limit laws. I've changed it from a limit into a numerical expression. So at this point, I'm just following the order of operations. You don't have to justify order of operations, just do it correctly. So from this point forward, I'm just evaluating. There we go, all of a sudden. So this is going to be 27 plus 2 is 29. That's going to be 9 minus 15 is negative 6. And 29 times 6 is 174, I hope. And since they're opposite signs, you get a negative.
Reminds me of identities.
It's just justifying steps. I mean, we justified steps and identities, so that part is the same. They're just different rules that we're using here. But again, there's several problems in your homework like this. These are the ones that get used most of all. 1 through 4, maybe 1 through 5. If there's a quotient, it's 5 instead of 4. And then 7, 8, 9 are the ones that typically use most for evaluation. All right, in that section. So you're going to get comfortable with those. If those do show up on a quiz, the yellow sheets will be usable. I don't expect you to memorize limit laws. I just want you to know how to use them. All right? Because again, when you're actually doing limits in real life, you don't use limit laws. You just do them. So this is good practice in understanding what you're allowed to do to limits. But when you actually do limits, it's not done with these laws. So I'm not going to nitpick on that too much. I just want you to get the practice and the homework correct. And if one shows up on the test, I want you to be able to do it.